Okay, so today we actually start with some of the actual MRI, getting slowly working in closer to actual MRI pulse sequences. And so today we're going to talk about how we can use the gradient, use a gradient for a slice selection. So this is, the idea here is to try to just activate a thin slab of the brain. And most people have a sort of a general idea of how it works, but just as important as the gradient is this idea of a frequency selective RF pulse. And so we'll start off talking about, basically how the gradient works. Then we'll have one equation for how we get a frequency selective pulse, and then we'll do convolution, the convolution theorem. We have to do all the greatest hits of engineering practical math, and so the convolution theorem is an important one. It's relatively easy to understand, and it's a way to sort of graphically think about the equations. So it kind of, instead of just messing with all the equations, you can actually get a nice sort of graphical intuition for what they're going to do. And so we'll finish up with that part. And then on Wednesday, I'll talk more about like fat saturation and other more complicated things related to the RF pulses. So start off with the gradient. So as I mentioned many a time, what is the gradient? The gradient is, it's just an addition onto the B0 field. So here's the person looking down on the person. So this dimension is the x dimension. Or we'll make it right-handed. So let's see which is right-handed. Yeah, okay. So there's the x dimension. So when you turn a gradient on, what does it actually do? Well, what it does is if you turn the x gradient on a certain amount, it adds a little ramp to the B field. And so if the B field is, say, going this way, so here's the B field. We're leaving a lot of it off, but the B field is up to here, everywhere. And so what the gradient does is it just adds a little increment, maybe 1/100th the size of the full gradient of the full B0 field, or subtracts an increment from this B0. So here's our B0, and then this thing we'll call it sort of the B gradient field, and we're only interested in the Z component of it. So this is the X gradient. So this guy is the X gradient, but the critical thing is it's affecting the Z component of the B field. So it turns out that's not actually possible to only affect the Z component. And if you look at the way Maxwell equations work for magnetic fields, you also have to, whenever you change the B field, you can't completely just change the B field and leave of the Z field and leave the X and the Y fields of the magnetic field untouched. And there are some correction factors that you can add in to sort of take account of that. But to a first approximation, we only care about the Z component of this relatively static field. So remember, the X and Y components are rapidly changing 100 million times a second with the RF coil, but the gradients can't change anywhere close to that. They're changing 1,000 times a second, and so you can sort of basically ignore sort of like the X and the Y component caused by the gradient, and so really in the B field. And so you're really only interested in this one here, which is the Z component of the B field that that the gradient adds or subtracts. So that's the gradient. So what is the main sort of main principle of how the gradient works? Well, it just changes the resonant frequency of the protons. And so if we make a plot here, so this is a plot, so this is the example I gave was of a z gradient. Okay, but let's just call this the x. In my notes, I think my notes have a z, but that could be x. So this is, so on this axis is, yeah, it's better to have it x. On this axis is the bz. So, and so we're looking at how does this bz change as a function of where you're on the x, and we just have something, it just goes up. It's a linear gradient, meaning it just sort of just adds, adds is a flat line onto this b0. So now what's the problem? Well, the problem is we want to select a particular slice. So we want to select a particular slice, and if you're using the x gradient to select a slice, what slice is that going to be? So that's going to be a sagittal slice. So, because if you consider for a given amount of the gradient, if it's an x gradient, it means that at that x point, it will all be the same. The resonant frequency will all be the same. But that's going to be true as you sort of come up in the, it won't be true, it will be true sort of going this direction. But what you're going to do is you'll select a slice that's perpendicular to the gradient direction. So if you had a z gradient, then you would select a slice that was perpendicular to the z gradient. So if you had a y gradient coming up and down this way, you'd select a slice that would be perpendicular to the y gradient. So that's what we're trying to do. And what does it mean to select it? Well, so what we want to do when we select is we want to sort of get a little chunk. So we want to get from this point on the gradient to that point on the gradient. So that's our slice in x. So remember, our slice in x is going to be a sagittal slice, sort of coming up and down like this, perpendicular to the direction of the gradient, the x gradient. So that's all good, but now if you consider we've got to actually feed in a little band of frequencies. So that's our problem for today. How do we get a band of frequencies? And so what frequency do we want to put in there? Well, we want to put in the frequency, we want to put in a band of frequencies, and that the band of frequencies will be that gyromagnetic ratio. Sometimes when you put the one way of just, this just stands for like 2 pi times this guy. So, sorry, I got that wrong. It's gyromagnetic ratio divided by 2 pi, yeah. Gyromagnetic ratio divided by 2 pi. So that's just so we don't have to have the 2 pi cluttering up things. So we can use frequency instead of the omega for radians. So we're using frequency. So when we use frequency, then we use this one, and we embed the 2 pi in this thing. That's just you'll see that sometimes in literature. And so then what we want is whatever the B0 field is. So what we're trying to find out is what is the frequency that we need to feed in order to select this particular slice. And it's going to be equal to whatever the B0 is. Here's the B0 there. And then, plus whatever the gradient, the z component of the B gradient. So this is just our original, the very first equation, which is just, omega, equals the, frequency times the B0. Frequency. The frequency equals the gyromagnetic ratio times the B0. That the very first equation that we ever put up. But it's a little more complicated than that because we don't actually just want one frequency. So what we want is a narrow band of frequencies. We want the frequencies that go between here and here. And so we don't want to just feed in a single frequency. We want to feed in sort of a narrow band of frequencies. And so how do we get that? Well, it's probably going to involve something like our sync pulse, because we know that if we do something in time that looks like this, so that's time, we know that Fourier transforms to a band of frequencies like that. So we're probably going to need something. This is going to be involved, but but if we think about it, it's a little complicated because we don't want a band of frequencies around 0. What we instead want is something like this. We want something. Wrong quadrant there. We don't want a band of frequencies around 0. We want a displaced band of frequencies like this. And, since we're in the Fourier domain, there's going to be some negative frequencies, but we'll just ignore those for now. So we want a displaced band of frequencies, not around 0. And so that's our goal. What do we need to do in order to get a narrow band of frequencies that's actually sort of displaced away from 0? Because that's what we need here. We need, from this frequency up to that frequency. So that's our basic problem of how to do this. Now, before we sort of get into what that is, let's just say a little bit about the gradient. So when we turn a gradient on, so one of the problems that immediately might come to your mind before we talk about how to get that narrow band of frequencies. So when we turn our gradient on, what does that do? What does turning the gradient on do? Well, it messes up the phase of all the spins. So as soon as we turn our gradient on like this, in order to try to select a pulse, we're going to immediately seriously damage all the spins because we're causing the spins at this side to precess at a lower rate, so their phase is all going to get behind, and the guys over here are going to precess at a higher rate, so their phase is all going to get ahead. And so immediately from the very beginning, we've got to deal with that problem. So when we turn on the RF, so here's the RF, and so we're drawing our RF like that. And so why do we always draw it like that? Because it's actually a sync. It's often a sync. That's why we always sort of make that little thing like that, little icon for it. So there's our RF, and which has to have this narrow band of frequencies. And then we have to turn on the gradient. So during the time that the RF is on, we need to turn the gradient on, like that. But now you can see what's the problem. Well, you just turned on a strong gradient, and that's going to massively mess up all the phase of the spins. And so what do you have to do? You have to immediately fix that. So how do you fix it? You generally fix it by putting in something that has the same area as that. So as half of what came before. So why half? So if you think of this problem, it's as we sort of dig into it, it gets worse and worse and worse, because you started, so at this point in time, there was no, at this point in time, you can assume, say, no transfers. Assume no transfers. So everybody's out, that means everybody's out of phase. Say there's no T2, hidden T2, it's just everybody's just completely messed up, and they're all evenly distributed around the XY circle. So now we turn on the RF pulse, and the RF pulse starts sweeping them together and sort of sweeping them together into some coherent oscillation. But it takes a while to do that. And now they're swept together in some coherent oscillation, but then the gradient is on, and the gradient is messing them up. So the RF is kind of like lining them up, and the gradient is messing them up. So how do you sort of figure that out? Well, it turns out if you do lots of equations, that you can basically fix up what got messed up with half. So we make this half area of slice select. So it turns out if you make this guy, the area of that guy, half of that one, why don't I just draw it? I'm drawing it the way it is in real life because you want to quickly get on with life, and so you generally tend to use a steeper gradient. But let me just draw an exactly identical one so it looks a little bit more easy to graphically see. Okay, so that one looks the same as that guy. So half the area of the slice select gradient, and it turns out that's a very good approximation that will take into consideration all the mess that I talked about, like, you turn the gradient on at the beginning and none of the spins are in phase, and then they start to become in phase, and then as more of them come in phase, they start to get out of phase because the gradient is on. It's a big mess. And so you can approximate that by just saying, let's turn on, we'll just assume that everybody got in phase right in the middle of this RF pulse, which is the biggest part of the RF pulse. And then if we make that assumption, then they would have had half of that gradient to get out of phase, and now we just reverse it and fix it. So you'll see when you start to look at MRI, there's a ton of things like this where you break something and you fix it. So this is sort of similar to gradient echo. You broke it over here and you fixed it. Why did you break it? Well, you needed to be able to set things up so you could feed in a narrow band of frequencies so that you could actually select a slice. So that's kind of the basic, if we were selecting like an X slice, then this would be the X gradient. So a lot of times we'll talk about selecting slices that are Z gradients. Those would be horizontal slices. Or they call those transverse slices a lot of times. This is we're selecting a sagittal slice. I put this up just so you definitely get the idea that you're not messing with the X the X gradient is messing with the BZ. Okay, so that's our basic. So let's label this. So this is a slice select. So that's basically slice select gradient. So let's now go to the more difficult problem of how do we get an RF pulse that has this displaced band of frequencies. So there's many ways to do this, as usual, and so we'll do the simplest one, which doesn't work well for like a 180 degree pulse, but it's a good approximation for a pulse that's like a 45 degree pulse or even a 90 degree pulse. And so what is this method? This method is it's the Fourier method. So we use I'll leave the gradient pulse up there for the time being. So it uses the Fourier transform once again. So let's write that. So this is first of three equations total. Okay, so here's the B1 field. So this is the XY component as a function of time. And so we're going to write that out as a Fourier transform of the frequency in the pulse. So this is time and this is frequency. So you can think of it as an inverse Fourier transform. So what we're summing across is all frequencies. So we're summing across our Fourier transform. So remember when we first wrote out the Fourier transform, we wrote out the Fourier transform as the sum across all time of this signal times the sines and cosines. This is exactly the same thing, which is just a sum across all frequencies for one point in time. And what we're summing here is however much we have at a particular frequency, and we're trying to solve for that, right? Because we want to actually know like what our frequency, or actually we're trying to specify that because it's going to be something that looks like this that we're going to put in for our distribution of frequencies. And then times our regular e to the minus I 2 pi frequency times time. Or we can reverse it, so 2 times time times frequency. So that you get an idea that we're doing the inverse Fourier transform. So basically this thing is just the FT. This is just FT, Fourier transform. So we're saying that and this thing is our, frequency selection function. That's what we want. I mean, that's what we're specifying, is this range of frequencies. And this is the time-dependent radio frequency stim. So so what do we need to do in order to get this frequency selection function? That's what this equation is telling us. And what we need to do is to take that frequency selective function, do the Fourier transform of it, and then that gives us our time-dependent sequence of things that we need to do to our RF in order to generate this frequency selection function. That's our goal. So if we solve this with the assumption that our probability of a particular frequency is equal to something that looks like this. So there's two things here. So we have the center frequency, and then we've got this thing, which is the frequency, what did I put, width. So there's two things. So there's the how wide the band of frequencies is, and then what is the center frequency. So this is frequency going in this direction and 0 there. So if we stick in one of those functions that we talked about, like the rect function, which is like this rectangular function, stick that in for here and then solve this thing, what do we get? So this is one way of getting it. We're going to get another graphical way that may be slightly more intuitive. So what the answer is, turns out to be, the Fourier transform of this thing. And what is the Fourier transform of that thing? Well, that's basically going to be some constants here, but it's going to be the sinc function. That was that function that looks like this, sine x divided by x. So the sinc function, there's a pi in there. The frequency width is in there again. The particular time point is in there, because remember, this is time. This guy's frequency. And then that whole thing is multiplied by a single frequency. So it's kind of reminiscent of when we were talking about the signal equation, how we end up with just one, or when we talked about sort of the FID, we just end up with one frequency, even though there's a mix of frequencies in there. So this is 2 pi fc. So that's, let me use the same cursive f here, f. Gotta get my typography correct. F, one last. Okay. Yeah, so this is just a single frequency. So, so what do we have here? This thing is a sinc envelope. So that's a sinc envelope at a particular point in time. And then this guy, sorry, I left out the t. And this is basically sines and cosines at a particular point in time. So this guy, these are the, the modulation, cos, sine, modulation. So that's going around the circle. And then at a single frequency. So it's kind of weird. So and this is just the, this controls the flip angle. That's the amplitude. Controls the flip. And then this one is the frequency width. So we get that's, the RF is going to have to be stronger for a wider width. So that's the answer. So the answer is it's a sinc envelope multiplied by a single frequency, which is the center frequency. And amazingly, that corresponds to an offset band of frequencies. So that's our answer. Now, how does that work? Sort of, it's a little bit, it's like the FID again. Like, how do you, you've got an FID. All these guys are getting out of phase. There's all these frequencies mixed together. You add them all up, and you get one frequency. It's just bizarre. Okay, so here's possibly a more intuitive way of trying to think about that. And it's kind of a more graphical way of trying to think about that. But the difficulty is it involves convolution. And so we have to talk about, and there's multiple uses for convolution. I should have left that guy on there, but there's multiple uses for convolution. So we're going to be talking about convolution again when we talk about the hemodynamic response function. And so so convolution is another sort of multi-use thing. But what we're interested in here is the relationship between convolution and the Fourier transform. So they have a very interesting relationship. But before we talk about that, so that's where we're aiming. We're aiming for sort of the convolution theorem, which is the relationship between convolution and the Fourier transform, in order to get our graphical solution. But first we have to do convolution. So what is convolution? So let's see, how many do I have here? Yeah. So we'll put our convolution over here. So convolution is another function. It's a little bit like the Fourier transform. So the first sort of intuition about convolution that's worthwhile is just like a Photoshop filter. So say you want to blur an image. When you blur an image, you're applying a convolution to the image. And how do you blur an image? Well, what you do is if you got an image here, what you do is you go to some part of the image, and then you look at points around that point and mix them in. So that's what a convolution is fundamentally going to do. It's going to sort of use some function, so like a circular function, to mix in data from nearby points. And you can see convolution, it's kind of like sort of turning inside out. That's kind of like the name of the convolution. So what is a convolution? So the convolution is basically, so the convolution at a point. So remember, just like the Fourier transform, like we said, the Fourier transform at a single frequency is equal to, it's a relationship between two functions. So in the case of the Fourier transform, we had the complex part of it, that was sines and cosines, that was kind of a function, and then we had the actual data, like the time series data, that was another function. This is kind of a case like that too, where we have two different functions. And so here's one function at a point in x, and then there's many different symbols people use for the convolution, so that one, we use that one for the convolution. And so here's another function. Let me just, not quite enough space. Let's move that over a little bit. Sorry, guys. So f of x equals one function, and this guy is our symbol for convolution, another function. And so the definition now is we sum across all of z, so that's a different variable. So for one point in x, we use a different variable to sum across, and our sum is the first function at point z times an offset point in the second function. So there's x, that's this x right here, minus z. So that's an offset point summed across all z. So look at our the summation. So here's what we're summing across, and it's there, and it's there. And what we're doing is we're doing the calculation for just for a particular point x. So there's that's the only x over there. So here's the x. So what this says is for one point in x, when we take these two functions and do this operation, we're going to have to sum across all of z. But just for this one point in x. So here's the one point in x, but z is changing across this summation. So if we draw that out, what does it look like? So one way of thinking of it is you can think of it as sort of an image. So we'll call this guy, so you can think of this guy as you can think convolution is commutative, so you can do it the other way also. And in the literature, you can sometimes they call G the kernel, sometimes they call H the kernel. It can go back and forth, but we'll call this the image, and then we call this the kernel. So this is like our blurring. You can think of this as our blurring filter, the G. So here's our image. So it's just a one-dimensional function. So there's our image like that, and this is our h of x, and this is x going in this direction. So now we take our function g, and what we want to figure out is for a particular point in x. So here's a particular point in x. So that's a single point in x that we're going to run this calculation for. So how do we do that? So for that particular point in x, what does this part of the equation mean here? So this part of the equation says, let's get our other function, which is our filter function. and put the 0 of the filter function lined up at this point in x. So there's x. And so now here's the z. And let's say our filter function is, I won't make it exactly go through 0 there. So if it was a blurring function like a Gaussian, it might go exactly through 0. So what is this minus z business doing? So what it says is, for one point in x, how do you figure out the value of the convolution? So remember, this thing is going to be equals something. So here's our output. So for 1x, so here's our output in x. So the way the convolution works is you go to a particular point in z, say, like this far away, in z. So, that far away. And then you go to this function, the kernel function, z, not minus z, but z. And so we just go that distance on the kernel function. So here, this is plus z. And then we go down and get that number, and we get this number. So those are the two numbers that we're multiplying here. We're multiplying whatever the image is at x with z subtracted off, and then we multiplying it by whatever this kernel function is at z, at this z plus z. And then we multiply them, and so that means we multiply these two numbers. Multiply those two numbers. So that's one term in this sum, and then basically just do that for the entire function. So that means so this guy, goes to there, and this guy goes to there, and like that, and that, and then right here, this guy multiplies by that one, and so you can see it's convoluted. It's very convoluted, isn't it? It's sort of, it's flipping it back and forth. And we'll explain why you do what the flip is for. But basically what you do is you do this whole sum, and then then it says, like, take that whole sum, sum that whole thing up, and then stick that in for one number here. So that's what the convolution is. So it just takes this. Another way of doing it is, you could say, that doesn't have the twist, is just take this function and flip it, and then do a correlation. So it is kind of a correlation again. You can see it's clearly a correlation. And in fact, if you change this to a plus, so here's sort of an interesting side point. So if we change to a plus, plus, then we get something called cross correlation, which is the same as convolution. It's just with the sign difference. Cross correlation. So what is cross correlation? Well, cross correlation would be take one function, say like this, and then take another function, a different function, say this is a different function, and then we could say, what's the alignment of this that gives me the biggest correlation between the two? If I put this, over here, run this kind of sum with a plus, put it over here, run it with a plus, run it, which one gives me the biggest value? So that's a cross correlation. So a convolution is exactly the same as a cross correlation. It's just a cross correlation with a flip. So if you change to plus, you get cross correlation. If you change to G equals H, then you get autocorrelation. And autocorrelation is another useful thing. That says, like, how similar is a function to itself. So why would you want to use that? Well, say you have say you have something that kind of looks like this. You might want to say, are these things spaced evenly? And so what you could do is you could take the exact same function and then do this convolution operation by switching it to all these different places and find out, do I see some oscillation in my output? So does that mean that this function is similar to itself at a distance? That's autocorrelation. That's another useful thing. So cross correlation. So this is this guy is convolution. So if you can understand convolution, well then it's the same thing as cross correlation, which is another useful thing, and it's the same thing as autocorrelation, which is yet another useful thing. So that's convolution. Okay, so moving right along, how does this, so that was just one point, and so how would you do the next point? Sorry, I should mention, just move this guy over a little bit, over here like that, and do the exact same thing, and then you get another point. And so eventually you'll build up a whole function by taking this g function and moving it to all these places on the h function. So this was the gc function here. Okay, so hopefully that wasn't too fast to be completely incomprehensible. But now let's talk about how it relates to the Fourier transform. And it relates to the Fourier transform. You can see it's sort of like the Fourier transform. It's going to essentially every point. It goes through every point in this g and h function to get one number. So it's very much like the Fourier transform. But the convolution theorem is that if we take the Fourier transform of two functions multiplied by each other, then that's equivalent to the Fourier transform of each function. I'll put t in there. It's better, yeah. No, let me do it the other way around, sorry. Yeah, I've straightened up my notes a little bit so that they're maybe hopefully a little easier to understand. So if we do the Fourier transform of two functions times each other, so these we're doing it in these guys in time, that's going to equal the Fourier transform of each one convolved with each other. So the capital means we've done a Fourier transform on it. So so the H capital means we've done a Fourier transform on it. Okay, so this guy means take Fourier transform, and then this guy to this guy. That means we took a Fourier transform of the function by itself, and this guy to this guy means we took a Fourier transform by itself. So what does that boil down in words? So in words, it means multiply in one domain is convolution in other. Because the Fourier transform is reversible, you can do it either time to frequency or frequency to time. So if we multiply in one domain, we do a convolution in the other and vice versa. So how could this possibly help? So let's use it to sort of figure out graphically why we get a sinc envelope. You get a sinc envelope with one frequency in it, and that corresponds to a band of frequencies. So, and I've straightened up the notes this year, so I've got frequency. I got time on the left and frequency on the right. So here's time on the left and frequency on the right. So our starting point is we want a band of frequencies. So let's just start with a band of frequencies around 0. We don't want that. We want it displaced. But how do we get it displaced? That's the goal. And so we know that this guy Fourier transforms into a sinc function. So here's our sinc function. So that's something we already knew. So this was time going this way. So if you have a signal in time like that, that corresponds to a band of frequencies centered around 0. So now our problem is, what do we want? We want this thing off to one side. And so what we want to do, we want to move it off to one side. So how do we move it off to one side? We convolve it with some spikes. So when you convolve something with a single spike, that's kind of like a special case. What it will do is it will basically just make a copy of this thing around the spike. So why is that? Well, if you think of the spike, if you think of this thing as the filter, and when you convolve it with this spike, it's going to blur this spike into something that looks like that. And so since the spike is only there, the result of this equals the result of convolving this thing with a spike is to just move it over here, which is what we want. Now, you've got to put a spike over here too, remember, because we got negative frequencies, so we're convolving it with two spikes. So we take our frequency band of particular frequency width here, centered around 0, convolve it with a spike. When you convolve anything with a spike, it's going to basically just make a copy of that thing that you're convolving with the spike wherever the spike is, because it'll be all zeros here. If you work through the convolution equation, everything will be zeros here, and it'll only be not 0 where it's within this width of the spike. So it just moves, the spike will make a copy of this filter function wherever the spike is. So now, remember, we can go back and forth with Fourier transform on all these. So this goes back and forth. So now we're almost there. So now we recognize this. This thing is what? It's just a cosine. So here's a cosine. So there's a cosine at 1. So it's just a cosine like that. Single frequency. But now you can use this thing. So if we convolve in one domain, we get to multiply, which is easier, in the other domain. So we get to multiply in this domain. And so what happens when we multiply our sinc? Here's our sinc. Equals, sine x over x. Then we get our answer. And so what is our answer? Well, our answer is an envelope that looks like a sinc. But it's got a cosine in it. This is cos. And so, what does that look like? That looks like, it looks like a little weird modulated cosine. Like this. So what does it look like? It looks like, starting here, you got a big sine, and it goes up and down like that, and then it goes small, and then it goes big again, and then it goes small, and it goes a little bit less, and a little bit less. So and then whoa. So amazingly, so it's got a single frequency. This is a single frequency. It's got a single frequency in it. But when you Fourier transform it, what do you get? You actually get something that has, a frequency width and at the center frequency. So now there's the center frequency, this is the frequency width. So amazingly, this thing, what is it? It's just you just turn the envelope of the transmitter on. So how does the transmitter actually work? What does the transmitter do? It just makes a single frequency. It just makes a single frequency. And what can you control? Well, you can control, what the frequency is, and you can control the amplitude, and you can control the phase. Exactly, where the zero is. So that's actually what the RF transmitter in the magnet does. It just generates one frequency, very good copy, quality one frequency. But then what does it do to make an RF pulse? It just generates that one frequency and then just goes like, woo, 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 woo. It just changes the amplitude of that one frequency. And then that Fourier transforms. So here's our Fourier transform. Amazingly, that Fourier transforms to a frequency band, which is exactly what we need in order to basically select a slice. So that corresponds to our little frequency band here. So that we can then essentially activate just one slice. So it's hard to believe, but that's actually the way the MRI works. It's got an RF transmitter that just generates a single frequency, the center frequency. And then this RF transmitter is carefully set up so you can instantaneously vary the amplitude of that one frequency. So this is the envelope here. But it's only got a single frequency in it, and then that Fourier transforms to a band of frequencies. So this thing is actually a band of frequencies. So this is the value of greatest hits in engineering. If you haven't done this before, it's just like magic. How could this actually work? But this is the way people often think about it. It's easier than dealing with all the equations. You just have a couple basic Fourier transforms, like a rectangle function goes to a sinc. We know some spikes go to a cosine and vice versa, and then we can come up with this complicated thing by this simple sort of graphical method of reasoning. So we powered through a great mess. We'll have some time to go over it on Wednesday, but I think we'll stop the recording, David, and ask for some questions.